Lovely. Then I can also ask my panelists to join me directly. In fact, yeah, as you have heard, we had a little change in the organization because unfortunately there was some chaos in the traffic in Munich this morning again. Therefore, I'm just taking over from Anna Elvense. I'm Jeanette Lorenz. So originally it was foreseen that I take a role in the panel, but now we do a little bit resorting here. So in principle, regarding my person, I'm head of department at Fraunhofer-Gesellschaft, looking at applications of quantum computing. I'm associate professor at LMU Munich, and I'm also leading the application side of the Munich Quantum Valley, a good connection to the previous talk. And in fact, given that our panelists have somewhat decided to give very long introductions to themselves in writing, I'm kind of too lazy to repeat that. Therefore, I first hand over in the row on how they are sitting here so that they can introduce themselves.
Okay, so thank you very much. My name is Thomas Hußlein. I'm a physicist by training, and I founded OptWare 25 years ago. And OptWare is doing optimization business since 25 years, so we transport mathematical algorithms into application, basically with large enterprises in the automotive and the pharmaceutical industry. And the quantum computer for us is a huge opportunity and also a challenge where there will be a disruption in our business of optimization. So we are very interested to be there in the very first place.
Yeah, my name is Ulrich Seyfarth. I'm happy to be here. I studied physics around about 20 years ago, especially quantum technologies, so I started on the topic quite early. Now I'm responsible for the quantum technologies at BearingPoint, so we are doing technology consulting, kind of filling the gap between the technology on the one hand side and on the other side the use cases. So in my team, people are understanding both sides, and we can connect people together. I'm happy to be here.
Yeah, thank you. My name is Sebastian Bock. I'm also a physicist by training, the next physicist in the round here. I work at Fraunhofer-Focus, located here in Berlin, and we work a lot on quantum software engineering, for example, developing high-level quantum programming framework Eclipse CRISP, also looking into several applications there, optimization, for example, and I think that's something we will also look into today and discuss today.
Yes, exactly. And now we would like to kick off the discussion, in fact, with a couple of slides. So, opening the topic, I will, in fact, show you very quickly what we are doing from the Fraunhofer side here. So, in fact, we have really many Fraunhofer institutes, as you are maybe aware of, and the Fraunhofer institutes that are looking more towards the software part and the application parts of quantum computing then organize themselves in the Fraunhofer Competence Network Quantum Computing. And basically, you see here a map of the different activities that we have there. They are in fact not complete, and in the end it also means that we have in all the regions, or at least close to everybody, let's put it like that, 9 regional centers that are then looking into applications of quantum computing and also into the software part on how we get there. You will also see that directly on the next plot that I'm showing. So the focus of this initiative is not, as you can see here, to build the hardware. Some other Fraunhofer institutes are doing that, in matter of fact. But our point is then we need to understand, and this is also the reason why we have now selection of our industry partners with us on stage, really to understand for what is that eventually useful. And in that sense, we cover really a very wide range of different fields of applications, for example, including logistics, the chemical sector, energy sector, basically anything that is reasonable to think of to do with quantum computing in perspective, although it is also a very essential part of our research, in fact, to understand what is sensible to do with quantum computing eventually. And in order to find that out, we then partner with very different partners. So, for example, on the hardware side, quite naturally, but then also with the software side, with the application side, so that we really can cover this topic in its different aspects. Then, of course, we also give our knowledge further and by then having dedicated training programs and participating in the education. So I leave aside the organization. In fact, you see it very nicely here in this plot that we are something that really like the bridge, if one wants to put it like that way. Yeah? Then we also really would like to understand, you see co-design here, very big, on how we can put things together and how we, in fact, then with the different components really make things working. In fact, that is also an aspect that we really would like to touch upon in the discussion that we have today, looking then, as you will see later, very specifically also about the collaborations and partnerships that we have. And in order to kick off this topic, we have now 2 pitches from our industry partners, starting, in fact, with Ulrich Seyfarth, BearingPoint, who are then giving a little bit more concrete details.
Yeah, thank you very much. Just to give a glimpse of how these projects can look like and what the ideas are, we brought a specific example here, which is a project that was which is owned by the QCI, by the DLR Quantum Computing Initiative. It's called QC Mobility Maritime, so it's trying to use quantum computers in the maritime environment and trying to use quantum computing to optimize inland freight shipping. Now, let's step away back and say, okay, what is BearingPoint doing? I mean, I was introducing myself a bit and showing a bit what we're doing. The important thing is here, I mean, we are a consulting company worldwide operating with the main focus in Germany, but we are connected to all the different market segments. So that makes it quite interesting if we have any quantum ideas, how to use quantum computers, we can use that in all the different segments. And what the part we are interested in here is called technology, so it's really helping clients to build their technology. There's a BearingPoint technology part which says, okay, how can we use software? How can we implement software so that at the end it can really be used at the client side? It's nothing from the stack which comes. It might be something separated. It might be something from the stack, but then all the business processes have to be adapted such that it can be used at the end. So this is our main task here. In there, I lead the team which is focus on quantum computing in that case here, but we also talk about quantum security, quantum sensing, so we're in all of these different areas. And the question is really how to use cutting-edge technologies, and for all of that we need partners. We need partners like the Fraunhofer, we need startups, we need research partners that bring the ideas, that bring the technologies, and on the other hand, of course, the expertise we have with the clients, so we can bring things together to figure out solutions. Now, let's go back to the project. You see there is a lot of different participants over here. There's 2 Fraunhofer institutes. There is Planck, which we've just seen in the talk beforehand, and everything is kind of given to us by the 2 different DLR institutions, so they are on the client side, and on the software stack here, on the coordination, we have different tasks for the different partners, and by our expertise as BearingPoint, we're involved in all of those. Now, as the project just started, let me give a bigger overview. So the project is included in something larger. It's the QC Mobility project, and questions are really focusing on to optimization of transportation and things like that. So we have air, road, rail, maritime, the project we have here, and also intermodal. And the question is how to get things into the different fields by looking onto similar use cases, which are all often in the transport area, which might be related to logistics, for example, which can be similar. I don't want to go into detail of all of these different cases. I want to focus here on the maritime, which is a specific and very, very concrete use case. So the second largest German waterway from Wesel to Datteln has several locks here. There is a few more, so there is 5 in total, but we just focus here on 3 of them. And what happens is that ships go into the channel from both sides. And of course, we want to maximize the throughput of these ships. in whatever sense. And by that, we want to use quantum computing. There is several tasks to be solved. So one task is how to fill up the ships into the locks. And of course, there's some restrictions. The ships come in, they park here at something like a harbor on both sides. They wait until this is cleared, and they can go to one direction and move the other way around. And as the canal is very small, overtaking is pretty hard, so this is the best pace to change the ordering. Now, yeah, this is modeling that we use. I mean, it's a standard method. It's nothing special that we do here for quantum so far in the whole process. Of course, there is quantum models that we use, so there is a real-world problem. We formalize that mathematically, and then we figure out how a model could be, and in this point here, we try to introduce quantum such that it is favorable for our solution. We model the solution, we get a real-world solution, and then we validate, we check whether it's working the right way, and whether we have whatever type of advantage. I don't want to go into what advantage in this case here means. There's several questions like the allocation, where to bring the ship to. There's several locks where the ship can go to. As I said, there's regulations. There's questions about placement, safety regulations I was already talking about. And in order to make things doable, as quantum computers are not that large to solve the overall problem completely, we need to make some of the things a bit simplified. So we simplify, for example, the placement. And then it's a question of what do we want to minimize. So one question could be how to minimize the longest delay of any ship. So the ship might go through with all the locks open and closing in the right timing, but of course you can never do that in the real case scenario if there's more ships. But still you can ask the question, okay, what about the ship that loses most? Can we minimize that? That's one of the questions we might ask. And then we continue that to get to our solution. So the project, as I said, started only a couple of months ago. We have already the first software implemented. So the first question was how to analyze the optimization problem. We did that. We evaluate an implementation. We have first quantum algorithms now selected, and we'll go that way. But I don't want to talk about algorithms here, so this is probably a bit more the part of the next speakers. As I said, we will evaluate the plans, and then if we realized how things work, so that's what's always important, to play around, learn, and then see how to scale, how to use, how to prioritize where's the best places to go into, and then extend that to more complex problems and figure out where we can really advance off that. Yeah, there's several different outputs, and by that, I would give to the next speaker. Thank you.
So thank you very much. I want to report on a project we did with Fraunhofer. The idea is, what drives us right now is to get into the realm of hybrid quantum algorithms. So we think that there will not be an impact, a sudden moment of quantum transition. It will be a smooth taking over. And for that, we need to decouple problems and get them into classical and quantum problems. And we wanted to investigate whether some algorithms are suitable for doing that. And we did this together with Jeanette and her team. And let me start. I'm a founder, so maybe I have some motivations here. I started being a physicist. You see, I was at IBM at a very cool time in the 90s. Where quantum computing was more or less developed and turned into their first computers having 4 qubits or things like that. Then I got very fascinated with optimization. I find this is a very basic principle in the world. Everything seems to go to its state of optimal. Maybe it's energy, maybe it's pleasure, or food, or it is shortest path. So I founded OptWare, and I started with mathematical algorithms. Later we added AI. We ended up in automotive pharmaceutical industry, which had very tackling problems, solving their complexity. And today we do both. We started with a task force about 5 years ago doing quantum. And we started with research projects, piloting projects with industry. And today we work on what we call the OptWare Hub, where we focus all our technologies in optimization, AI, and quantum computing to make scalable solutions for optimization problems. So just the logos, where our customers are. I always say smallest customer has 2 billion in revenue. So we do long-term partnerships. We often do large projects where we solve the processes that get optimized and also do all the infrastructure, getting the data for the process, getting also the workflow for the different people working on the process, so an optimization result really can be useful. So what's driving us? So there's a huge, let's say, breakup moment coming for the optimization business. So far, it was always having two things. You had to involve human intelligence to model, to write algorithms, and then on the second hand, you needed computers. And with more intelligence and faster computers, things evolved rather smoothly. But now you have two major technologies that are on the verge of getting useful. The one is artificial intelligence, which really is already in use. I mean, we see this huge transition right now. And for the computer, quantum computer promises a really impact on speed. So what's our thing? I've written it already. We think we must get quantum ready now. With this promise of a huge impact on computer power, we think quantum computing will have an impact. So we start, as I mentioned before, setting up hybrid quantum computer systems. And of course, we still have an open technology race. We just heard about neutral atoms. There are other technologies. And we must understand which technology is the best fit for the best project. And of course, we must prepare the IT infrastructure to make things useful and usable. So make quantum computer usable. So we want to have user experience, solution quality, and quantum readiness. I think I speed up a little. So what did we do in the project? We have, as always said, we have an industry problem, we have a modeling, we have quantum computing, and we want to get this all in the OptWare Hub to make it scalable. That's our issue. So we have used an improvement on the mathematical modeling to get the decomposition of the models better. So we have the problem that when we want to scale that, a lot of the things must get automated. So we must have, for instance, a use case identification. We must identify what is important, what kind of mathematical model, what method is suitable, and then, of course, decompose the model. And we want to get this automated. We want to get the, let's say, consultant, the expert, as much out of the loop as it is possible. And that's my last slide. No, my very last slide. Get into quantum. Get quantum ready. And I really mean that. I mean, I'm not a prophet that says, oh, there's a doomsday coming. I'm just saying there's a new world coming, a new technology, and get ready for it. And thank you very much. And I give to the next speaker.
Yes, and so with these kind of pitches, I think we have set good grounds for our discussion. We were already circling now a lot around the question of collaborations, and I would like to start with this aspect and deepen it further. So maybe, in fact, we should start with the non-industry in this particular case. And Sebastian, if you could maybe summarize from your experience what kind of collaborations do work, how do we set them up, basically, between almost academia, namely Fraunhofer, and industry to make value.
Yeah, I mean, there's on the organizational level, there's of course multiple ways you can collaborate together. There's some research projects you could apply for together and work in together. There is some more industry projects where as a subcontract you could work together, you give some insights to a company or so on. But I want to focus a bit more on the application side, on how to properly work together then independently from the organizational or management part. Because, for example, we have seen the log scheduling problem. And what you have there is that you have someone working in this area, having some application or some problem, and then saying, hey, maybe we could do quantum computing. And you have seen this is a very, very complicated problem. You could go in very, very great depth there. You can say, okay, which ships should go into first, how can we arrange them in the log. You could also have some overtaking within the channel, and you can add some priority for some ships, so you can go very, very complicated problems. But you have to somehow get together from both sides, from the quantum computing side, quantum computing experts. They have to understand these complicated problems first, and the other side has to understand, okay, what can we maybe do with quantum computing? So you have to really sit together, get and get a common understanding of what we can do, and start to speak each other's language. And this typically takes some time, but that's something you have to start with at some point in these kinds of projects together.
Yes, a very good point. Before I would like to deepen that point a little bit further, a general remark to the audience, in fact. So we are not completely strict with the points that we discuss here. So if you have other points that you would like to discuss, then hopefully there is somewhere a microphone, and then I take you then according to the interest, etc. We already have one intersection, in fact.
Yeah, maybe. Thank you. Yeah, so really fascinating, these optimization problems. However, there are also classical methods, right? Linear programming, mixed integer, and so on and so forth. Do you exhaust these first and then go into quantum? Is that, yeah?
So that's actually what we are doing in this project. As Uli presented already, we have some first implementation, and this is a classical implementation. Yeah. So that's the baseline we start with to really do some classical optimization, and then go to the quantum realm, so to say, and check some optimization, some different algorithms, and apply them to this problem. Yes.
And a follow-up question, those can be solved in quantum-inspired algorithms, but then also, of course, in quantum machines. Do you also do, let's say, quantum-inspired on GPUs for those, or do you go directly on quantum computers?
Not directly quantum-inspired, but really use classically existing solvers. So we have seen some other talks where they use some quantum-inspired MPS simulations, for example. That's not what we're doing here. We're using some existing C-plex solvers, for example.
Okay.
Yeah, but matter of fact, taking this up, and then also I'm happy if Thomas then also comments, this is a general pattern that we see and that we also need to have, because in the end we want to create value. It is not about bringing a certain technology forward in the end. It is really about creating value. And that means the first ingredient of creating value is to really understanding the problem. Then, after having understood the problem, you of course want to solve it. We are researching, we are testing, we are pioneering on how to solve that with quantum computing. But if we are seeing that this is not the way forward, then a quantum-inspired method or classical methods might be better suited for the case. And a matter of fact, what we see is that there is an immediate business benefit by having understood the problem very well, and then to putting forward a classical method as well. Nevertheless, it's a shade of grace, one even would like to say, and Thomas, this is in fact very exactly the reason why we partner with, in fact, you're not application industry in that sense. You're something that one could put into a proposal, a solution provider, to exactly do this.
Yeah, actually for us, providing actually what we sell is a solution to a problem. And for the customer, he doesn't want to know how it happens. Actually, he wants to get the best solution. So with all this packaging of software in services and cloud computing, it gets irrelevant more and more how things are getting done. So for us, an algorithm must decide, do I go to the GPU, do I go to the quantum, or do I just solve it linearly? And sometimes this might also, beyond the solution time, it might be economical, and maybe it's cheaper to go to the classical and wait an hour as go to a GPU and go do it within seconds, or go to a quantum computer and have it maybe in milliseconds solved. So for us, there's a huge park of new technologies that all have to be integrated, and not just saying, oh, I'm a physicist, quantum is cool, let's do it with quantum. I mean, that's not a business.
Do we have here other comments?
Yeah, maybe I can add a bit to that. I mean, there is not the standard organization, there is not the standard client. I mean, we have different sizes of clients. Some might invest into an internal team that will, in the future, be knowledge of solving problems with certain methods. So they might need to understand how quantum works, what the upsides and downsides of this quantum computing is. I mean, there's two sides for me. One is like this learning. Do we want, and if these organizations need that, do we need to learn how to use problems, how to understand whether, I mean, especially if we want to be in the real forefront, how can we understand, how can we prioritize, how we can identify use cases in organizations such that we can take advantage out of that. And I mean, this is one part, and the other part would be the question, okay, I have a problem, I want the best solution for that problem in whatever 1 year, 2 year, 5 year oversight, so I might even adapt to the future, be able to adapt, and this is why quantum inspired might especially come into place then. And then, of course, it is an integration of all, as it was already said, of all these different technologies, whether it's a standard CPU, whether it's the coprocessor we were talking 20 years about, whether it's a graphics card, whether it's, I don't know, a photonic quantum chips, whether it's, again, which type of quantum technologies. I mean, all of them also have different use cases, right? So this needs to be integrated in the long term.
So while the audience is maybe thinking about more questions, I would like to tune in on the point, what do we need in terms of resources, personal and technological wise, to make that happen, in fact, within companies, the kind of this transit to understanding the interplay of the technologies, often really integrating the technologies. Maybe Thomas, you would like to start?
Yeah, I mean, that's a very, very, very difficult question to answer, because what you see is we create something very complex. I mean, when you integrate 3 different technologies of computers, let's say, let's keep it there and not add more, then we need an easy access to these systems. I don't want to become an expert on how to run GPU systems. I don't want to become really an expert on anything, so I need somebody that provides this for me with an easy access. Basically, it has to be in the cloud. And then, of course, I have all these different technologies in optimization and modeling and AI, so I need a pool of experts that can contribute, and that's really the point about it. I mean, I think there's not many organizations in the world that can have all the knowledge and in there, but I think there's a big ecosystem in Germany and in Europe that can provide all this knowledge. So it's more a method of orchestrating that and getting the IP things right to get this done, I think.
Sebastian, you want to add?
Yeah. I think that's a very good point, because if you look at many companies, there's some very well educated people. There's engineers, there's computer scientists, there's mathematicians, and they have a very well understanding of the math you need for quantum computing. So you have a very good starting point to get into it, to educate them a bit, and there's also good educational material. There's good educational material for free even available if you just want to get started. There's so many things you could get into, or there's also many research institutes or Fraunhofer institutes or already some startup and companies who are looking into this who could give guidance to where to start. And I think this is a good point for companies who haven't yet started, who maybe are not in the audience here, so maybe a call to action for everyone. Just spread the word. I mean, we are very much consolidated in the quantum computing network here, so you see each other again and again. But if you know someone new who might be interested, also spread the word. I mean, we have seen it on your slide, Get Ready Now. Everyone here has seen it, but people outside of this room haven't. So this is also something which is also important to get more people educated there, to get more people interested.
So just as a reminder, if you have any kind of questions, please raise your hand, because otherwise I don't see it. So I would now like to get a little bit mean to our panelists and ask, to myself as well, and to ask the most critical question. I mean, as we have now heard, and we also know from our own research, quantum technologies is some kind of not decided game. We don't know exactly if it will fly. We have certain expectations and hopes, but if working really very hard on the algorithmic details, we also know about the devil in the details. And now there are quite some people arguing, let's first develop the hardware. Don't worry about the aspects on how to make it working on the software and algorithmic side. So what would you say, in fact, now both from your company and research expertise, but then also maybe from the outside view of somebody, some company who thinks about to get started in this kind of field? Why should one worry about software and applications? Thomas, you're the prime candidate to answer this.
Yeah, well, what's the answer? The answer is, if you want to integrate, I mean, the value of a quantum computer doesn't come from I can build this thing, but I can run applications better on it. That's the value of it. Or I can go to new solution spaces, which I wasn't even thinking of tackling so far. So I need the software stack, actually, in my view, be ready before the quantum computer is ready, because there will be a fast race. I mean, this glass with the goldfishes was a little funny, but there will be a fast race when this thing becomes available. As you see with AI, this thing is suddenly available and everybody runs. And why are all running? Because, I mean, the competition in the industry is very fierce. Very, very fierce. So if I can have an advantage over my competitor, let's say in production cost of 10%, and only sustain that for a year or half a year, I shoot the other guy out of business. And that's what really, I think, drives the thing. Get ready. And of course, the machines have to be ready, but the applications have to be thought through before, I think.
And looking at the time, I would, in fact, like to take this question as a kind of closing word. So maybe, Sebastian, you would like to continue, and then we go back into the middle.
Okay. Yeah, I just want to add on and go to the starting point. The problems you want to solve, they are complex, so it needs time to understand them and to understand how to map them to a quantum computer to then get this maybe 10% advantage over the competitor. So that's another reason why you should just start now. Problems are complex. Otherwise, you could solve them with a classical computer already. So that's the reason why you have to go to these complex problems to actually do something with a quantum computer you couldn't do before. And yeah, you have to get a feeling also. Also, the people at the company should get a feeling of what you can do, why it makes sense, and you have to do so early on, implement this early on, because new technology, it takes time, even especially if you are a bigger company, to really employ this into your processes. It just takes time. So getting started earlier makes sense. And we have seen the roadmaps from IonQ, from various other vendors. They really sped up. So it will be here sooner than I expected 5 years ago, for example. Yeah.
So business is about innovation and risk. And we need to understand there is an innovation needed from us as companies because of a development with some probability will come in some time, right? So of course we need to play here on the risk card in some sense. But we see how many money is put into that system, And we also see the progress. And the important thing is the progress is exponential. We saw the exponential progress in AI, and people were like overwhelmed of how fast it suddenly appeared. But it did not suddenly appear. It was there for a long time, but no one realized. The same happens here. And again, people will be suddenly overwhelmed how fast this is. So the best thing we can do is really analyze how important that is for organization you're working in, how fast you think this is going to happen, and what do you think? I mean, how should you prioritize the different areas in the organization that need to adapt and that need to learn? And what is very important is to educate. And educate doesn't mean to educate on the physicist's level to really understand how things are working. Education is here really related to how deep the organization is either related to simulation, and then it might be quite deep to the physics or to the chemistry or whatsoever, or if it's more in optimization, or if it's more something in the organization that can be done with outer sources. But that needs to be done. Understanding the problem, realizing how important the problem is for the organization, and then step forward.
Yeah, and maybe adding to that and getting back also to the scientific side, given that we have now covered very many aspects, I would maybe also close with an example of our own research on this aspect. So, for example, people in machine learning think or speculate that maybe quantum computing is only useful for quantum data. So you find this kind of speculation in various literature. You don't find a little bit good solid statements, but you find the speculation. Yeah, and so, for example, my group is researching what is one part of our research, what properties the data, the classical data, need to have such that you can even hope to get a quantum advantage. Yeah? And this is then a very fundamental piece of research to some extent. I'm sure that Uli would be most happy to have the answer, because then he could directly kind of outscope probably 70% of the requests that he get, if that is feasible or not, before even kind of starting. Yeah? And this is the kind of example of a transit that we are now doing, and this kind of information we in fact need to have for any kind of forward developments on software application and hardware side as well. So with that, many thanks to the panelists and for your attention.